Hello everyone. Okay, let's go for lecture 17. All right. Okay, how is everything going? Yes, I know you guys are under stress. Okay, it's just everybody is, but we are going to study and then stay focused until we finish the semester. Fortunately for this class, okay, most of you are passing, and many of you have a really good grades. So I want you to maintain your work ethic, and your good records until the end. All right. So lecture 17, calculate on probabilities of events. So in this case, we are going to use there are three kinds of probabilities, logical probabilities. So we do not experience anything. We don't have to experience anything, and we are not going to be given some kind of a table or data from other people so that we can work on. Instead, we are going to start from scratch and then think, okay? So experiments with equally likely outcomes. So that means this time, in order to think in our heads, some things like different situations or different circumstances, we cannot really handle that. So let's say, when you roll a die, you are going to have, well, what is the probability that you are going to roll a 1 or roll a 2, roll a 6? Well, that is all equally likely to occur, 1/6, okay? Or when you toss a coin, yes, we are going to say, okay, what is the probability that you are going to toss a head? We are going to say a head. Well, that means just a 50-50, just 1/2 of a chance. So things like that, so we can think in our heads and then calculate, okay? If that is the case, how do we calculate the probability of event E? Well, in this case, again, nothing will be given to us. So we are going to say, hey, event E is the number of outcomes in event E over N, big N. So here, the big N is number of outcomes. Guess what? The entire space. So that is in sample space. Okay? So let's say this is the sample space, and this is event E. So what is the probability that event E occurs? All the outcomes have an equal likelihood. Okay? So that is well, every outcome has equal chance to occur. Therefore, just the number of outcomes in this case divided by the number of outcomes in the sample space. That's how we do it. Okay? So, well, the complement rule. So, for example, this is the event E. Of course, the outside is what? E prime. So, E prime, so probability of E prime is the same as 1 minus probability of event E. Okay? So many times we are going to use this fact. Okay? So, ready? Example 1. I'm going to remind you that this probability of event E prime is 1 minus of probability of event E. Okay, so example 1. Selecting balls from an urn. So an urn contains 8 white balls and 2 green balls. So altogether, how many balls are there? 10 of them. I always want you to write down 10, okay? Even though very simple math, of course, okay? However, when you calculate this, you do not make any mistake. All right, so here, a sample of 3 balls is selected at random. Sample of 3 balls. Okay. I want you to recall this. In the previous chapter, what he did is, there are this many balls in the urn, and then we are going to make a sample of 3. How many samples can be made? That's what we did. Okay, so here, this in the previous case, we had the number of samples. What was that? Combination 10 choose 3. That was the answer, and we are going to use that. Okay, so I'm going to just leave it there. This time, what is the probability that just contains only white balls? Only white balls in the sample. So think about it. As a probability, okay, this number of samples, the entire number of samples is this, 10 choose 3. In this case, this event, you see only white balls in the sample. So what does that mean? All the white balls, 3 of them came from here. Nothing came from green, correct? So, how do we set up? This is going to be the entire case, just regardless of color composition, number of samples, that is 10 choose 3. And only white sample, so that is 8 choose 3. So this is how you set up. So that is the number of outcomes in the event E, and this is a number of outcomes in the sample space. Does it make sense? Okay, so this event E means you have a sample, just you see only white balls in the sample. That is the event. Okay. So everybody remembers what that is? Okay. We are going to compute, and then A choose 3 is 56 over 120. I assume that just by now you know how to do it. I don't have to. 0.467. So roughly 47% of the time you are going to see just white balls in the sample. Okay? See, almost half the time. Why? Because there are a lot more white balls than green balls. Okay? And if you want to make sure, A choose 3 is, you can compute this one, A choose 3 by divide by 3 factorial if you did by hand. So that is 8, 7, 6. You start from 8 and multiply downward, and you multiply this many numbers. So 8, 7, 6, 3 numbers, and then stop. And then 3 factorial is 3, 2, 1. So 6 cancels this. Therefore, 56. That's how you get 56 over here. Okay? So, the next one. Part B. What is the probability that sample contains at least one green ball? Okay, I am going to write over here probability that only white balls. That was 56 over 120. Okay. So this time, what is the probability that at least one green ball in the sample. One green ball in the sample. Let me think. At least one green ball. That means one green ball or two green balls. Correct? If there is one green ball, that means there are two white balls in the sample. If there are two green balls, that means there is exactly one white balls together, because we have to make a sample of 3. Okay. But I don't want to do this way. So instead, I'm going to think about the complement. And that is very beneficial, especially if you see the word at least one. So let's rephrase this. Probability that at least one green ball. So how can you say that? That is, green ball is present in the sample, correct? Green ball is present. Yeah, at least 1, 2, 3, doesn't matter, okay? Green ball is present. So when you switch to complementary, we can say 1 minus probability that, what is a complement case? Well, we are going to negate it. Green ball is not present. Make sense? Okay? The complement case is green ball is not present. What does it mean? You just rephrase it. Green ball is not present. That means there are only white balls. Only white balls in the sample. And we already did, correct? Okay? So that's why we want to take advantage of that. So that is 1 minus, here is 56 over 120. So that is 120. So this one you change it to 120 over 120. So that gives you 64. Okay? So once you compute that, that is 0.533. Earlier it was what, 46.7%. So roughly 47%. Yeah, this one is roughly 53% of the time. It's going to, you are going to see at least one green ball. Okay, so this complement idea, okay, I'm going to separate over here. The complement idea is really useful when you see the word at least one. Okay. Next. Quality control. Yes, now we see some sign of that. Okay, is we are going to use mathematics in industry. A toy manufacturer inspects boxes of toys before shipment. Each box contains 10 toys. Okay. So example 2. So imagine you are working at a factory line and your job is to inspect toys in a box. Each box contains 10 toys. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 toys over here. Okay. The inspection procedure consists of randomly selected 3 toys from the box. I'm going to pick up 3 toys randomly. If any are defective, the box is not shipped. Okay, of course. Yeah, you don't want a bad thing to the market. Suppose that a given box has 2 defective toys. Yeah, it's unfortunate, but yeah, the manufacturing process did. Like this toy and this toy, these 2 are defective, let's say. Okay? But we cannot tell just when you just look at them. All right, what is the probability that it will be shipped? Okay, summarize again. There are 10 toys in a box, in each box, and you are going to select a sample of 3. sample of 3. If anything you see in the sample is defective, you discard the box. Okay? So discard it. Discard the box if any is defective. Makes sense, right? Okay? And there are 2 defective ones. And you are an inspector. Well, when are you going to ship it? Just you select only 3 of them. So if you select 1, 2, 3, these 3, then you are going to think that, oh, this box is okay, and pass it. Why don't we do not inspect every single thing? Because it takes time. That means time is money. You need more people to inspect each box. Therefore, for that kind of practical reason, we cannot do that. Okay? So are you ready to set up? So what is the probability that this box is shipped? This particular box is shipped. So again, why this box is shipped? Because only good ones are in the sample. Can you say that? Only good ones or good toys are in the sample. That's why you ship it. Just put the pass, just stamp, and then let it go. So only good ones. So what is that? It means it's the same as only good ones or good toys in a box. So now we are ready to set. Well, this one, there are 10 toys, but there are 2 defective ones and 8 good ones. So all these 3 are from these good ones. Make sense? So what is the probability? That is, how many samples can you make regardless of defective ones or good ones? There are all 10 in the box, so that is 10 choose 3. So that is number of all possible samples. Just number of just samples. That is 10 choose 3. And just the samples that have just only good ones, that is 8 choose 3. Okay, so did we do this list before? Yes. I'm sure we had in the previous problem, part A. That is exactly the same. So that is 56 over 120. So that is again 0.467. That is roughly 47%. So let's recap this. The previous one and this one sounds totally different. The first one was about just some green balls and what kind of balls was that? Green balls and white balls in an urn. And here it is toys. So sounds different, right? Okay. However, what you want to notice over here is that there are 2 different colors, and the color combination was 8 and 2, 8 white balls and 2 green balls. Here 10, again 8 good toys and 2 defective toys. There are 2 types, good ones and defective ones. That's why you are going to see the same solution over here. The next, let's think about, if you own this factory, would you be satisfied? So imagine this box goes to the market. Okay, so that means your nephew or someone is a lot younger because there's a toy playing with the toys. Okay, yes, just your nephew or your niece got the toy and that toy is defective. Wow, those kids, little kids will be very, very upset. Yeah, I remember I had to go to, my son received a toy for Christmas, and guess what? It was not working. So next day, as soon as I got up, I had to go to Toys R Us and return it. Of course, there are a lot of people. So imagine, these companies, they do not want that kind of things to happen. So what do? They have to really inspect. But in this system, yes, 47% of the time, this one will go to the market. So how can they improve their inspection process? Probably, what? Rather than make a sample of 3, what about sample of 5? But if you increase to sample of 5 over here, this number will be a lot more. Okay? You can make a lot more samples, yes. And it's going to take a lot more time, and it costs too much. Yes. Okay? All right. So this is one problem related to quality control. Okay. The next one. This time, selecting students. Okay, example 3. Selecting students. Again, sound very different over here. A professor is randomly choosing a group of 3 students to do an oral presentation. In her class of 10 students, 2 of them are on the debate team. Okay, so 10 students. So instead of 10 toys, this time 10 students. It's not about male or female. 2 of them are on debate team. So 2 of them are on debate team. So 8 of them are not on debate team. Okay? What is the chance that the professor chooses at least one of the debaters for the group? Well, the professor is selecting, select 3 at random for a presentation. So what is the probability that at least one of the debaters for the group? Okay, so what is the probability that at least one in debate team is selected? Okay? So, again, do you remember that? If you see at least one, it is better switch to the complementary. Okay? So, that is 1 minus at least one in debate team. So what is a complementary case? The opposite case. The opposite case is no debate team is selected, right? So probability that, okay, just only